Engineering Predictive Analysis (CFD) Simulation. Predictive analysis plays a key role in the early design stages for the selection of optimal solution regarding manufacturing modeling and assessment testing results. This step is the integrated application of scientific and mathematical knowledge. Here, we make use of the computer's powerful numerical analysis capabilities through 3D modeling, complete several design solutions, and convert them into mathematical models and finite element analysis to assess the design solution's pros and cons. On the screen, what you see is the compressed air racing car that we completed. The effects of airflow cannot be seen through the naked eye, so we use mathematical 3D data to calculate within the software under the speed of our vehicle how airflow influence on the car body causes speed and pressure variations. Through the speed and pressure variations, we can assess the car body's efficiency in terms of fluid mechanics and aerodynamics to serve as the basis for our initial solution assessment, which is also the corroboration of scientific evidence. In the engineering design process, theory is used as a method of design decision-making. In the Living Technologies in-depth course for the engineering design project, we integrate both 3D modeling and predictive analysis as important methods for our design decision-making, which compared to the method of trial and error, design prototype assessment that you previously used, there will be a huge difference. In the process of engineering design, namely the proposal of design solution, it is suggested that students use 3D modeling as much as possible because this method can produce the mathematical model data that we need, and through the software's computing and analysis functions of this mathematical model data, we can use the scientific evidence we have evaluated as the decision-making assessment of the design. This concept is called predictive analysis. After going through predictive analysis of the design solutions, we select a solution and then produce a prototype. This way, we can save a lot of time and resources wasted if the solutions were made one by one. The next step is to actually go into prototype manufacturing and the subsequent testing and techniques. This kind of process in our engineering design is the ability that students need to deepen their learning. This brief explanation through picture in the project's predictive analysis stage, it is mainly performing design research. For the compressed air racing car, we use a high-pressure steel cylinder to give out a fixed amount of force. The supply of this force allows our vehicle to produce different maximum acceleration based on different design forms. Under this premise, we hope that the design of the body of our compressed air racing car is more in line with the efficiency of fluid mechanics and aerodynamics so that it can achieve our goal with the least traction and the best stability under higher speeds. This concept is an important design premise for us to do predictive analysis on the car body. Based on this premise, draw up different design solutions and perform assessment and finally select a solution for further design and manufacturing development goals. Before proceeding with the predictive analysis of the vehicle's fluid mechanics, let's have a conceptual introduction to vehicle's motion and aerodynamics. When a vehicle is running at a high speed, the airflow will produce a great force on it. Whether this force is exerted in the front or rear of the vehicle will cause many alternating effects on the vehicle's motion. We will use this picture on the right to illustrate these affecting forces. Here we can see that when the vehicle is running at high speeds, with the incoming airflow, the vehicle's front and the windshield will produce front impact that reduces wind speed and increases the pressure to the red state. For the air coming at the hood area, the roof area, and the vehicle's rear area, that creates vortex vacuum. The speed of the air passing through will increase and the pressure generated will decrease, even reach a negative pressure. So under these changes in airflow and pressure based on the car's side, lift force will be created at the hood, and there will be downforce at the car's front and windshield areas. The roof part of the car has lift force and the rear part of the car has an even greater lift force. These forces will have some positive and negative effects on the stability of the car. In the design of the compressed air racing car, we want the vehicle to produce less traction when passing through a strong airflow, that is, the red area. which we want it to be reduced as much as possible. But, on the other hand, we also hope that the lift generated by the green area will not have a negative impact on the stability of the vehicle. Especially in the rear part, these two conflicting design goals require a design decision that brings balance and optimization, yet allows the compressed air racing car to reach our design goals in the fastest way with the lowest drag. From concept explained before, you can see that the aerodynamic design of a vehicle is different from that of an airplane. In terms of aircraft design, when flying, it is hoped that the wings can generate a lot of lift when passing through the airflow to overcome the weight of the aircraft itself and allow the aircraft to fly mid-air safely and with stability. The design of the vehicle requires appropriate downforce so that when the vehicle is passing through high-speed airflow, it does not drift and causes instability on the car. Especially for racing cars, downforce provides the vehicle with a stable handling performance and sufficient driving capacity of the tires to maintain safety and stability in high-speed driving. This is the difference in aerodynamics design between vehicles and aircrafts. Let's have a look at a sports car with an outstanding aerodynamic design, the Lotus Evija. Its many original design methods in aerodynamic design can provide students with reference for future compressed air racing car design. Next, let's have further introduction and comprehension of vehicle aerodynamics. First, let's introduce the concept called drag coefficient. The higher the drag coefficient, the greater the affecting force of the airflow passing through, the greater the traction force. For example, on the bottom left picture, there are 6 basic geometric shapes, and the drag coefficient on each geometric shape passing through airflow is different. For example, for a disc shape, its windward area is very large, so its drag coefficient is very high, which is 1.1. If it were a high concave hemisphere, its surface area is even larger, so its drag coefficient is even higher, reaching 1.4. This sphere below has an air drag coefficient of 0.45. We often know about a shape called a drop shape, and you may often hear that it is the shape with the lowest drag coefficient. But this shape, when faced at different directions, its drag coefficient will also be different. From this graph, we can see that if the sphere part of the drop shape is faced windward, its drag coefficient can achieve the lowest value among all shapes. Many fluid mechanics related designs that must achieve a minimum drag coefficient are often designed in the shape of a drop, such as a submarine, a hot air balloon, or solar-powered or fuel-efficient cars that must save energy yet remain fast. They are all designed in the shape of a drop. The main reason for this shape design is because it has the lowest drag coefficient among all shapes. The picture on the right shows the different vehicles on the road, from cars and sports cars with a low drag coefficient around 0.3 to lorries and trucks with a coefficient of more than 1. You can roughly determine the drag coefficient based on the shape. However, the actual drag coefficient value requires a lot of measurements with scientific instruments or computer simulations to obtain a more scientific-based data. In the following picture, we can get a rough idea of the proportion of air drag and traction in a vehicle. The top half of the body, shown in pink, it accounts for about 45% of the air traction. The area around the tires under the car roughly accounts for about 30% of the air traction, and lower body portion of the car roughly accounts for about 20% of air drag and traction. So overall speaking, for the design of a car, apart from the shape of the upper portion of the car, the design of the lower body portion and around the tires is also very important, and it must be considered as a whole. In our handout, we have provided some design principles for the reduced air drag design of the car body. There are 17 design parameters regarding the car body style design for your reference. Next, we will introduce you to the software Flow Design used for fluid mechanics analysis and what observations can be done on vehicle aerodynamics. After we have completed the 3D modeling, the model is converted into mathematical data and imported into the fluid mechanics analysis software. In the fluid mechanics analysis software, we mainly focus on three aspects. One is the overall traction of the vehicle's body shape. In other words, air drag. The second one is whether the vehicle has enough downforce when driving. The third one is the vehicle's stability and balance. In this picture, we can see the calculated value of the drag coefficient of some small-sized vehicles using the fluid mechanics analysis. The design of this racing car has a more flattened body shape with a reduced windward surface area which can achieve a lower drag coefficient. If it is a van or a truck, regarding its drag coefficient, in addition to having a larger windward surface area, the unstable airflow at the back of the van is greater. This kind of airflow often results in higher drag coefficient. For the downforce observation, it can be done in the racing car aerodynamics kit. In its pressure distribution, look at the red areas, that is, its positive downforce pressure, whether it can effectively transfer the force down to under the wheels to serve as an important force for the vehicle's stability control. In the fluid mechanics analysis software, in order to observe the vehicle's stability and balance, open the model's pressure distribution graph and observe whether the color distribution of the left and right halves of the vehicle is evenly distributed, especially for the racing car, which emphasizes on the downforce's even distribution. The pressure distributions in the front and back and the balance between the left and right are all important aspects to observe. Next, like the students on the screen, we will import the 3D model we finished into our fluid mechanics software Flow Design, evaluate the performance of the model. At this stage, using this software, students are to perform analysis and simulation on the images required to obtain for the engineering notes and capture the data obtained. Regarding the operation, students can watch the tutorial video demonstrated by the teacher. For image capturing, we need to capture the airflow image, as this picture is shown, where we can see the model of the compressed air racing car as well as the airflow variations caused by air flowing through the car. Second, we also need to capture the pressure distribution graph. We should put the compressed air racing car in the front position and look at the pressure distribution map on the left and right sides and capture this image. Third is the overall airflow and pressure distribution graph. Here we try to adjust the vehicle's perspective view to one in which the front and back can both be seen, and display the airflow and pressure distribution equally on this vehicle at the same time, and capture this image to our engineering notes. Next is the traction and drag coefficient image. This will serve as our main assessment of the differences, advantages, and disadvantages of different models in terms of aerodynamic performance. We also need to capture this image and record it in our engineering notes. In addition, if students have some special designs to improve aerodynamic efficiency, you can capture a close-up image of the variations in its aerodynamics and record them in our engineering notes. Hello everyone, here's a demonstration of fluid mechanics analysis once we are finished with our 3D modeling to evaluate its aerodynamic performance. We will first frame select our completed model and use the group action to turn all the originally separate models into a group. Then go to Files and select Export Selected. Choose the STL file format. The file name is recommended that you type it in English so that errors are usually less likely to happen when importing to other software. Press Save. For the STL format, we choose this 0.01 default format. For the file type, we choose binary because the file size is smaller. Next, we switch to the free flow design fluid mechanics analysis software from Autodesk. We select and import the file we need to analyze from our local desk. Select the STL file we just saved, and our model will be imported into the fluid mechanics analysis software. At present, what you see is the airflow in a plane. If we want to see a more comprehensive airflow distribution, we can click this icon in the middle and switch from 2D to 3D operation mode. Here, students can see that our car body is surrounded by airflow on the left and right sides. In the analysis of aerodynamics, we mainly look at three aspects. One is drag, that is the resistance of our car body to the airflow. For a compressed air racing car, ideally it would be as slow as possible. Another aspect is balance, that is, whether the left and right sides of our car body are balanced, so that the performance of the vehicle will be better, and it will not be easily disturbed by the airflow and causing drifting issues. The third one is what racing cars particularly take importance on, which is the downforce, whether it can create higher downforce on the aerodynamic components in both the front and rear wheels so that the vehicle's handling is good and the driving at high speeds is safer. How do we interpret these data from the software? Next, the teacher will make an explanation one by one. What you can see at the upper right corner of the screen is the information of our model and the wind speed given for our test conditions. The upper left corner is the speed color of the airflow, which represents the speed of the air. Here you can see that red means that the speed is faster, and blue means that the speed is slower. In the design of our compressed air racing car, we can clearly see that in this curved section on the roof, and some of the airflow at the back have red streaks, which means that when our airflow passes through such a curved surface or exists these parts behind the car body, there will be an acceleration phenomenon. There are a lot of fluid mechanics factors involved here. How do we look at the traction generated by the airflow on our model and the drag coefficient? We open this icon on the top middle, the drag graph. When you open this command, we can see that a statistical graph is shown. The data shown is based on the finite element analysis done on our model in the software. Here we can see that our drag coefficient is changing between 0.85 around 0.84 and the traction force is about 4 newtons. This force is a calculated data according to our model size at a wind speed condition of 10 meters per second. This is a more scientific and objective value when doing predictive analysis. If you want to capture this data into our engineering notes, open the drop-down menu at the top left corner of the command row. You can save this screen as either a dynamic video or an image. Click on the Save Image to save to the file format we want, such as Save a Test1 JPEG file. And this picture will be captured, and this data will be used as a scientific basis for the prediction analysis assessment. Here we'll also make a conceptual comparison. Many students may think that we can reduce the drag of our car by adding a horizontal wing at the front of the car or a spoiler in the back of the car. We'll use the same model and add a spoiler to compare the differences in traction and drag coefficient between the two models. The teacher will switch to a racing car model with a spoiler. Its model size is the same under the same wind speed condition of 10 meters per second. We can see that the drag coefficient has increased to between 1.14 and 1.15, and the traction has also increased to 6 newton. So adding a spoiler does not actually reduce drag and traction. Instead, it has increased its effect on airflow. Why do we need to add these aerodynamic components? The main concept idea is to improve the stability of the vehicle, which is related to the concept of balance and providing more downforce pressure that will be covered later. Regarding the balance of the aerodynamics of the racing car, we'll open another file for explanation. Here we have imported a Le Mans-style compressed air racing car. Regarding balance operation, we need to enable the 3D dynamic simulation display and allow the airflow to pass through the car body completely. In addition, we need to enable the surface pressure display. Here we rotate the compressed air racing car to an orientation where we can see a balanced symmetry between the left and right sides. Regarding balance, we mainly observe the colors displayed on the car. See if the color distribution of the left half and the color distribution on the right half are equally distributed. The color shown here, if the color that you see is red, it represents the area with higher pressure, followed by yellow and then green. If you see a blue-colored pressure value, it may be negative pressure. That is, the airflow speed is very fast. Previously, when we talked about airflow streamline, we knew that red meant that the airflow is faster, and the roof will show red streamlines. So regarding pressure, the speed is inversely proportional to pressure. So where the airflow speed is fast, the pressure on our car body is shown in blue, which means that the pressure is low or negative. So for the design of this Le Mans racing car, we can see that it has some designs that require the airflow to provide positive pressure for the car and improve the stability of the body. Such as the lateral curvature of the wheel arches, we can see that the pressure distribution in this area is positive pressure, which will transfer this force to the front wheel so that the downforce of the front wheel becomes higher. That is, its friction against the ground, positive pressure on the ground is higher, and the steering control performance and stability will be better. Similarly, for the spoiler at the rear of the car, we can also see that it shows orange and red areas. The left and right sides are symmetrical. It also provides a lot of downforce here, so that the rear of the car can improve its stability, and the grip, handling, and driving force of the rear wheel will be better. Finally, here we will demonstrate in this predictive analysis phase after using fluid mechanics software analysis. What kind of data do we need to record into our engineering notes? First of all, what you can see on screen is the streaming distribution of the airflow passing through our compressed air racing car. Here we will move the car to a lower position and adjust it to the angle that we need. Capture an image and name it Streamline Distribution. Next, we will open the 3D simulation screen and also enable the surface pressure display. We'll rotate our car to the front of the vehicle, rotate slightly forward. We can capture this analysis image to surface the balanced pressure distribution symmetry image of the vehicle's left and right sides, so we will save image and name the file pressure distribution. Adjust the model to a perspective view. Here, we can fully see the airflow passing through the compressed air racing car we designed, displaying each part's pressure and airflow. Let's capture this into an image and name the file Airflow and Pressure Distribution. Then we open the drag plot statistical data and move our compressed air racing car to an appropriate position and angle. Here we can see that our drag coefficient is 0.59, traction is 0.1 newtons. The average drag coefficient is 0.62. We also save this image to serve as a reference for our predictive analysis data. The name of the party is Traction and Drag Coefficient. If you want to save any images of special parts such as airflow of the spoiler, we can switch to 2D mode to adjust the position of the airflow passing through the car. Let's scale out a bit. There is a ball over here, which is the planar coordinates of the airflow. We can adjust its position so that the airflow can be directed to the edge of our spoiler. We can use some close-up images to show what kind of changes happen when the air flows through the edge of the spoiler. We can also save an image of it and name the file Spoiler Airflow Effect. After capturing these images, we can import another compressed air racing car that we have designed to make a comparison between 2 or 3 models. This is the engineering prediction analysis of the compressed air racing car using fluid mechanics software.